this episode, we're going to make sense of the moving parts inside a control system that beginners often see as a blur of numbers, labels, and mysterious status bits. When someone first looks at an OT interface or a controller view, it can feel like everything is happening at once. Signals appear to flip, values change, alarms come and go, and names like tags and timers show up without explanation. The good news is that most of this complexity is built from a few repeating ideas, and once you understand those ideas, the system stops looking like chaos and starts looking like a set of understandable conversations. You will learn how to track inputs and outputs, how watchdogs and timers fit into reliable operation, how current values should be interpreted, and why tags are more than just labels. None of this requires you to configure anything or memorize vendor-specific screens, but it does require you to build a clear mental model of what the controller is watching, what it is commanding, and how it remembers what happened a moment ago. When you can follow that mental model, you can reason through OT scenarios with confidence instead of guessing. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Inputs and outputs are the basic handshake between the physical world and the controller, and they are often shortened in conversation as inputs and outputs, I/O. Inputs are signals coming into the controller from sensors, switches, and other devices that report what is happening, while outputs are signals leaving the controller that command actuators, alarms, and other actions. Beginners sometimes think of inputs and outputs as wires, and while physical wiring can be involved, the deeper idea is that inputs and outputs are points where the controller learns and acts. An input might represent a temperature reading, a pressure switch state, or a safety interlock condition, and an output might represent a motor start command, a valve position request, or an indicator light. Inputs and outputs can be discrete, meaning they are on or off, or analog, meaning they represent a numeric range. The controller's logic reads inputs, evaluates rules, and then writes outputs, repeating that cycle continuously. If you keep that simple loop in your head, you can interpret many OT behaviors by asking, what is the controller seeing on the inputs, and what is it trying to do on the outputs? One of the first places beginners get confused is mixing up what is commanded with what is confirmed, because the controller can request an action and still not receive evidence that the action actually happened. For example, an output might command a motor to start, but an input might confirm that the motor is running, and those two signals can disagree if the motor fails or if a protective device prevents startup. That disagreement is not an error in the controller's thinking. It is a real situation the controller must handle. Many systems include logic that checks for confirmation within a time window, and if confirmation does not arrive, an alarm or a safe fallback may occur. This is why it is dangerous to assume that an output state tells you what the equipment is doing, because output state often tells you what the controller wants, not what reality is. Similarly, an input might show a condition, but you must consider whether the input is healthy and whether it reflects the real process state. Beginners become more accurate when they separate three ideas: the command issued, the feedback received, and the actual physical outcome. This separation matters for safety, troubleshooting, and security, because attackers and failures can target any one of those points. Another beginner trap is forgetting that inputs and outputs can exist in layers, meaning a single physical signal can be represented as multiple internal values in the controller or supervisory system. A sensor might produce an electrical signal that becomes a raw value, then a scaled engineering value, then a filtered value used for control, and each of those could appear as a different internal reference. Likewise, an output might exist as a requested command, an actual output signal, and a status that indicates whether the actuator accepted the command. These layers exist because controllers and OT software are designed to manage imperfect reality, such as noisy sensors, calibration requirements, and actuator limitations. When you see multiple values that seem related, it is often because one is closer to the raw signal and another is closer to the processed meaning. This is also where misunderstanding can lead to wrong conclusions, like thinking a process variable is unstable when you are actually looking at an unfiltered raw input. A calm way to handle this is to ask what the value represents, what it is used for, and how it is derived. If you can answer those questions, you can track signals without getting lost in the volume of information. Watchdogs are another concept that helps systems stay reliable, and beginners can think of a watchdog as a simple guardian that checks whether something is still alive and behaving normally. In many OT contexts, a watchdog is a timer-like mechanism that expects a regular sign of life, such as a heartbeat signal, a periodic update, or a recurring task completion. If the sign of life stops, the watchdog assumes something is wrong, like a software task has stalled, a communication link has failed, or a device has frozen. The system can then take a predetermined action, such as triggering an alarm, switching to a safe state, or preventing outputs from changing unpredictably. Watchdogs matter because controllers and networks are not perfect, and a silent failure can be more dangerous than a loud failure. Beginners sometimes imagine that if a device fails, it will obviously shut off, but many failures look like the device is still powered while it is no longer thinking correctly. A watchdog helps detect that kind of failure quickly, which supports safety and operational stability. From a security perspective, watchdog behavior can also be a clue, because certain attacks or disruptions can cause communication or processing to stall, and watchdog events can become early signals that something abnormal is happening. Timers are closely related to watchdogs, but serve a broader set of purposes, and they are everywhere in control logic because physical processes often need time-based behavior. A timer can delay an action, limit how long an action can continue, confirm that a condition persists long enough to be real, or enforce a sequence that must wait for stabilization. For example, a system might wait a few seconds after starting a motor before checking a running feedback input, because checking too soon could create a false alarm. A system might also require a level switch to be active continuously for a certain duration before treating it as a true high-level condition, which helps ignore momentary noise or turbulence. Timers can also be used to prevent rapid cycling, such as turning equipment on and off too frequently, which can wear components and create instability. Beginners sometimes think of timers as simple clocks, but in OT they are often safety and reliability tools that shape how logic behaves during transitions. Under stress, timing becomes even more important because processes can respond slowly, communication can be delayed, and equipment can take longer to reach steady conditions. When you track timers in your mind, you start to see why a system might look slow on purpose, because patience can be a control strategy in a physical world. Current values are the moment-by-moment readings and states that show what the system believes is happening right now, and they include both numeric values and Boolean states. Numeric current values might include temperatures, pressures, flows, positions, and speeds, while Boolean current values might include interlock states, permissives, alarms active, and device readiness. Beginners often assume that a current value is inherently trustworthy, but a mature approach treats it as a report that depends on the health of sensors, communications, and processing. A current value is best understood as the system's present belief, which may match reality closely, or may be delayed, noisy, or wrong if something upstream is compromised. Another common confusion is mixing the value itself with its quality indicators, because many systems provide flags that indicate whether the value is good, bad, stale, or out of range. Even without seeing a particular interface, you should understand the idea that values can have both content and confidence, and both matter. A control decision made on a value with poor confidence is risky, and many systems include logic to handle that, such as falling back to a safe mode or holding the last known good state. For exam scenarios, recognizing that current values can be healthy or unhealthy helps you avoid simplistic answers that assume numbers are always correct. Tags are the names and references used to represent these values and states throughout the OT environment, and thinking of tags as mere labels will cause confusion because tags are more like identities. A tag links a concept, like tank level, pump status, or valve command, to a specific signal source and to the places where that signal is displayed, stored, alarmed, and used in logic. In many environments, tags are used consistently across controllers, HMIs, historians, and reports, which makes them the threads that tie the system together. Beginners sometimes assume tags are arbitrary, but tags usually follow naming conventions that encode meaning, such as location, equipment type, and signal purpose. Those conventions help humans navigate complex systems, and they also help software organize data reliably. Tags matter for security because changing what a tag points to, changing how it is interpreted, or changing who can write to it can change system behavior in subtle ways. An attacker might not need to rewrite an entire program if they can influence a small number of critical tags that drive control actions or visibility. Learning to treat tags as meaningful identities, not just words, is a big step toward understanding how OT systems stay coherent. A concept that helps tie inputs, outputs, current values, and tags together is the idea of a scan cycle, meaning the controller repeatedly reads inputs, evaluates logic, and updates outputs in a consistent loop. The scan cycle is a rhythm, and many system behaviors make more sense when you imagine that rhythm in the background. If an input changes, the controller sees that change on the next read, then logic responds, then outputs are updated, and that entire chain can happen quickly but not instantaneously. This is why you might see brief mismatches, where an input has changed but the output has not yet reacted, or an output has changed but the feedback input has not yet confirmed. Beginners sometimes interpret these transient states as errors, but they are often normal timing effects of the scan cycle and the physical process response. Timers and watchdogs exist partly because the scan cycle is not enough by itself to guarantee safe behavior during unusual conditions, such as when a device stops updating or a feedback signal fails to arrive. Tags provide a stable way to reference what is happening within that loop, so humans and systems can talk about the same signals consistently. When you keep the scan cycle in mind, the system feels less like a set of independent parts and more like a coordinated routine. Another common source of confusion is mixing up where a value originates, because a value displayed on a screen might come from a local controller, a remote device, a historian, or an intermediate system that aggregates data. In some cases, what you see is a direct live value from a controller, while in other cases, what you see is an updated value that is pulled periodically, which can introduce delay. Under normal operations, small delays may not matter, but under stress, delays can change decisions, especially when alarms are involved or when operators are making rapid choices. This is why many OT systems differentiate between real-time values and archived values, even though both may look similar in a display. A historian, for example, stores time series values that are useful for trends and investigation, but that stored value might lag behind the live control value. Similarly, a supervisory system might show a value that is refreshed on a schedule, which is fine for monitoring but not ideal for fast control. Beginners become steadier when they ask, is this value used for control or for observation, and how fresh is it expected to be? That mental habit reduces misinterpretation and makes it easier to understand why certain systems are segmented or why certain communications are treated as sensitive. When control systems are under stress, the relationships between these elements become more visible, and that visibility can be used to reason about what kind of problem is happening. If outputs are changing rapidly while inputs remain stable, that can indicate noise in internal logic, a misconfiguration, or a feedback signal that is not being trusted. If inputs are fluctuating wildly while the physical process should be steady, that can indicate sensor issues, interference, or data integrity problems. If watchdogs are triggering, that can indicate a stalled task, a device freeze, or a communication failure, and in security contexts, it can also indicate a disruption event. If timers are frequently expiring, that can indicate that expected confirmations are not arriving on time, which might be caused by equipment performance, network latency, or incorrect assumptions in the logic. Tags can help trace these relationships because they provide consistent identities for signals across the system, making it easier to see what changed and where. For beginners, the goal is not to diagnose like a specialist, but to recognize patterns that suggest whether the problem is measurement, command, confirmation, timing, or system health. Those categories are often enough to answer exam questions accurately because they reflect how OT teams think about reliability. Security and safety intersect strongly in this topic because the same mechanisms used for reliable control can be targeted or manipulated to cause confusion. If an attacker can write to a critical tag that represents a set point or a mode, they might induce stress by forcing the system to chase a moving target. If an attacker can spoof input values, They can trick the controller into making wrong output decisions, essentially turning the loop into a weapon against itself. If an attacker can disrupt communications, watchdogs may trigger and systems may fail over into modes that reduce visibility or capacity, creating operational risk. Even without an attacker, poor access control or poor change discipline can create similar outcomes, like an accidental tag mapping change that causes a display to show the wrong sensor, leading to wrong human decisions. Beginners should understand that OT security is often about protecting the truthfulness and stability of these signals, not just about blocking external threats in the abstract. A stable, trustworthy signal flow is what allows operators to keep the process safe under normal conditions and under stress. When that trust is broken, the system can become harder to control even if nothing appears physically damaged. This is why OT security emphasizes controlled access, accountability, and careful handling of changes to logic and tag configurations. A practical way to keep all of this straight is to anchor your thinking on the questions a careful operator or engineer would ask when something looks wrong, because those questions naturally map to the concepts you are learning. The first question is what the system is seeing, which points you to inputs and current values and the confidence of those values. The second question is what the system is trying to do, which points you to outputs and commanded states. The third question is whether reality agrees, which points you to feedback inputs and confirmations. The fourth question is whether things are happening in the expected time, which points you to timers and the timing assumptions built into logic. The fifth question is whether the system itself is healthy, which points you to watchdogs and heartbeat behavior. Tags tie these questions together by giving consistent names to each signal, which lets humans and systems communicate clearly about what is happening. When you use this questioning approach, you reduce confusion because you stop staring at a wall of values and start organizing them into a narrative. That narrative is exactly what many exam questions are testing, because OT security scenarios often revolve around interpreting signals, constraints, and safe responses. To close, tracking inputs and outputs, watchdogs, timers, current values, and tags without confusion is really about learning the language of control systems and the way that language stays organized under pressure. Inputs and outputs, I/O, define how controllers sense the world and act on it, while the separation between commanded outputs and confirmed inputs keeps you honest about what is wanted versus what is real. Watchdogs provide a safety net for silent failures by detecting when devices or tasks stop behaving, and timers shape logic so that transitions and confirmations occur in safe, realistic time windows. Current values provide the system's present belief about process and device state, and learning to consider freshness and confidence prevents beginner mistakes where numbers are treated as unquestionable truth. Tags provide the identities that let all of these values be referenced consistently across controllers, displays, and records, which is why they matter for both operational clarity and security integrity. When you hold these concepts together as one coherent model, OT environments become easier to understand because you can follow the flow of truth, commands, and time-based expectations. That clarity is exactly what you need for Security OT+, because the exam is designed to see whether you can reason about how OT systems behave and what can go wrong when signals, timing, or trust are disrupted.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.